Hello everyone, welcome to Broadview. My name is Joseph. Today we're going to discuss an age-old question that no scientist or philosopher has been able to fully explain. What is time? Michel Besso was Albert Einstein's best friend. He passed away on March 15, 1955. After hearing the sad news of Besso's death, Einstein decided to write a letter of condolence to the Besso family. In the letter he wrote, "Now he has departed from this strange world a little ahead of me. That means nothing. For us believing physicists, the distinction between past, present, and future only has the meaning of an illusion, though a persistent one." 1 month later, Einstein died in his sleep at 76. Einstein's quote later got summarized into a phrase: "Time is an illusion." Now, is time an illusion? Where is the end of the universe? Well, there's a long story behind this, so let's get started. In 1989, NASA did a crazy experiment. A volunteer named Stefania Fellini was isolated in an underground cave with no concept of time. The experiment was initially set for 210 days, but it came to an end after 131 days. The cave was located in New Mexico, only 30 feet below the ground. Stefania spent the 131 days without sunlight or sound from above. The researchers built a room with an area of 18 square meters. Inside the living area, Stefania had all of the necessities of life, as well as lots of books to read to spend the time. In the absence of sunlight, she could not tell when it was day and when it was night. She also didn't have any other way of measuring time. The researchers used cameras to monitor her experience 24/7 and regularly collected her blood and urine samples for testing. She had the option of terminating the experiment at any stage by pressing a button. The researchers promised her a reward of a generous amount of money after completing the experiment. Stefania was 27 years old at the time. She came from Italy and worked as an interior designer. She was selected out of 20 candidates. NASA liked her introverted personality and strong self-discipline, hence why she was selected. On January 13, 1989, Stefania moved into the cave. At first, she was curious about her new environment and interacted with it. She spent the time reading, exercising, and tidying up. At first, she regularly ate 2 to 3 meals and slept for 8 to 10 hours a day. But as time went on, her biological clock drifted away from its regular rhythm. At times, she could only sleep for a couple of hours, while other times, she slept through the whole day. She was able to stay awake for more than 20 hours even. To ensure that the experiment could continue in a healthy way, the researchers sent her additional entertainment, including a guitar, a computer with simple games such as solitaire, but no time display, and 2 pet rats. Stefania communicated with the researchers using the computer. The experiment came to its 90th day. Stefania told the researchers that she's doing all right, but through the camera, the researchers could definitely tell something wasn't right. She looked so miserable all the time and stopped reading the books. She stopped playing with the pet rats and only played on the computer mechanically. She would go on without eating much for a few days. After drinking water, she fell back to sleep, only to wake up again after a day's sleep. By the time the experiment reached the 100th day, Stefania's period also became irregular. The researchers offered her vitamins and drugs to improve her health, but her body was still getting thinner and her condition worsened each day. On the 120th day, she looked like a completely different person than when she had first entered the cave. Her eyes looked dull, she did not eat nor communicate with the staff outside. For hours on end, she stared at a corner of the cave without moving. The staff was worried that she might die if it continued like this, so they called off the experiment when it reached 131 days. Stefania came out of the cave on May 22, 1989. Countless people, including scientists and journalists, were present at the entrance of the cave to witness her rebirth. Overjoyed to see the light of day again, Stefania faced the reporters and said,
"Wow, man, I love the sun. It is beautiful."
During the 131 days, she lost 7.7 kilograms of weight. Her muscle strength and calcium levels were reduced, and her immune system definitely declined. When asked how long she thought she had been in the cave, she believed that she had only been there for 2 months. But in fact, she was in the cave for more than 4 whole months. Although she received a generous compensation, she became extremely insecure, easily dazed, and paranoid for a long time thereafter. She said she would discourage anyone from participating in this type of experiment because the feeling of timelessness was lingering. Initially, NASA did not design this experiment to prove that time is an illusion. It was aimed at examining how the stresses of long-term isolation could affect space travel. After all, during space travel, astronauts often need to stay in the capsule for months. NASA was interested in finding ways to avoid physical discomfort for the astronauts. But the results of the experiment have proven, from another perspective, that the human perception of time comes from observing the changes of the external references. For example, the passage of time can be observed in the ever-changing positions of the sun, the moon, and the stars. Researchers also deduced that even if a clock were placed in the cave so that Stefania could tell the time, the results of this experiment would still be the same. Without external references, the times written on the clock would just be meaningless numbers to her. The results of the NASA experiment happen to be strikingly similar to the view of time put forward by the ancient Greek philosopher Aristotle more than 2,000 years ago. In Western history, Aristotle proposed the earliest classical view of time in his book Physics, around 300 BC. Now, in simple words, Aristotle believed that time is a measure of motion. In his view, the existence of time is not absolute, but relative to the change or motion of objects. For example, it takes 0.1 seconds for a bullet to hit its target after being fired. The 0.1 seconds is a measure of the change between firing and hitting. If there's no movement in the world, there would be no time. Some people may argue, no, that's not true. I lie in bed at night and the room is dark, so nothing has changed. But how come I can still sense the passage of time? Aristotle said that movement could also be inner feelings. At night, our body is not moving, but our brain's active. That's why we can still experience the passage of time. Objectively, time is associated with motion. But Aristotle believed that time is also subjective. For example, we feel that time flies when we are focused on a task. In today's time, Aristotle's view of time still seems straightforward and intuitive. But in the 17th century, another great figure in physics challenged Aristotle's view of time. In 1687, Newton proposed the concept of absolute time. Newton believed that time was absolute and independent of objects and their changes. He believed that time would still pass by on its own rhythm, even if the universe was empty, or if the objects remained perfectly still, or even if there was no brain activity at all. Newton's absolute time was a revolution because it conflicted with Aristotle's view of time. But since Newton's laws of motion became so successful and popular, it gave credibility to his theory of absolute space and time. For a long time, his assumption became the dominant view of modern science. In Newton's view of space-time, time is a uniformly passing entity with no beginning and end. Matter moves and changes in space-time, while time and space are independent of each other and have nothing to do with matter. Newton used to represent time in his physics equation. The equations that later got derived from the Newton's laws of motion still uses the letter T. In fact, at the time, many scientists and philosophers opposed Newton's theory of absolute space-time. Gottfried Wilhelm Leibniz was a German mathematician and philosopher. It's said that Leibniz's original name, Leibniz, had a letter T in it, but because he was convinced that Newton's absolute time, T, did not exist, so he removed the letter T from his name. In the early 20th century, Einstein introduced the theory of relativity and brought another revolution to the view on space-time. We've all learned in physics classes that the speed of light is constant. Today it seems like common sense to us, but hundreds of years ago, this question haunted scientists for a long time. We know that the speed of objects is relative. For example, a train may move with a speed of 80 meters per second, while a person inside the train walks in the same direction at a speed of 1 meter per second. Then, an observer on the platform would see that the person on the train is moving at a speed of 81 meters per second. The speed of light should follow the same logic. But in 1887, physicists Albert Michelson and Edward Morley conducted an experiment. The results proved that the speed of light is constant, in fact. For example, take a look at the stars. If the stars were stationary, then the speed measured from the light emitted from the stars would be the normal speed of light. Now get this. If the stars are traveling towards the Earth at a certain speed, then when measured, the speed of light should be the speed of light itself plus the speed of the stars flying to the Earth. But in fact, the measured speed of light did not change. That is, regardless of whether the stars were stationary or moving, the time for light to reach the Earth is the same. In other words, the speed of light remains the same. So how is this possible? The Michelson-Morley experiment caused an uproar in the physics community. Many scientists have jumped in to try to explain it, but none of the explanations made much sense because the explanations were still based on Newton's absolute spacetime. It wasn't until the beginning of the 20th century that physics giant Albert Einstein ushered physics from the old century to the new. One day in May 1905, Einstein passed by the famous Burns clock in the city center on his way to work. When he heard the clock striking, he was suddenly inspired to think about how the clock behind him would time itself if he were moving away from the clock tower at the speed of light. Because the light reflected by the clock also travels at the speed of light, it would never be able to catch up with Einstein. That is, the time on the clock would forever be the time seen before Einstein started moving away. Its hands would no longer turn, and it would be as if time had come to a complete stop. But the watch on Einstein's wrist would still keep time as usual. Instantly, Einstein figured out the answer to the Michelson-Morley experiment. The speed of light is absolute, but time is relative. In 1905, Einstein put forward the theory of special relativity. He proposed that absolute time does not exist. In the world of relative time, the faster the speed means the slower the time, which demonstrates time dilation. This slowdown can be understood through this example. You are doing gymnastics in a high-speed spaceship, but looking down at you on the ground, it would seem as if you are in slow motion. But you would feel that time does pass by normally. 10 years later, Einstein published the theory of general relativity, which incorporates gravity into the framework. General relativity shows that the greater the gravitational force, the slower time passes, which also demonstrates the concept of time dilation. When the theory of relativity was first proposed, many people found it unbelievable. And some even said that the theory of relativity discussed the cheapness of the speed of light. This is because the conclusions drawn from the theory of relativity can only be felt at a speed close to the speed of light. But the speed of man-made objects is far less than the speed of light, so who knows if this theory is right or wrong. In 1971, two hardcore physicists, Joseph Haffel and Richard Keating, did an experiment using cesium beam atomic clocks. Although the speed of man-made objects cannot catch up with the speed of light, the difference can be measured with ultra-high precision instruments. For this experiment, atomic clocks were taken aboard commercial aircrafts, while the other atomic clocks remained on the ground at the United States Naval Observatory. The aircrafts flew around the world near the equator. While one aircraft with atomic clocks flew eastward along the equator in the direction of the Earth's rotation, the other flew westward against it. Each flight lasted for a period of 3 days. Finally, the time on the atomic clocks on the aircrafts were compared with the atomic clocks on the ground. Atomic clocks are the most advanced timepiece. They only have an error of 1 second every 20 million years, so they were chosen to measure the changes in time relative to movement. When the plane flew towards the east, it had a faster speed due to the Earth's rotation. So the relative speed difference between the two flights would be larger and more convenient for observation. According to the theory of special relativity, the faster the speed means the slower the time. Theoretically, the atomic clocks on the aircraft flying along the direction of the Earth's rotation would be slower than the atomic clocks on the ground. In addition, according to the theory of general relativity, the smaller the gravitational force means the faster the time. The atomic clocks on the plane were at high altitude, so the gravitational force would be smaller. So this means, theoretically, the time on the plane should be faster than the time on the ground. In this experiment, the planes flying at high speed and high altitude took both Einstein's general and special relativity into consideration. Okay, what was the result of the experiment? After several days of flight, the atomic clocks on the eastbound plane, that is, along the direction of the Earth's rotation, were an average of 59 nanoseconds slower than those on the ground. And the atomic clocks on the westward plane were about 273 nanoseconds faster than the clock on the ground. Before the experiment began, Haffel and Keating had also calculated the predicted values of the effects of gravity and velocity on time, respectively. The experimental results proved to be very close to the predicted values. Both Einstein's general and special relativity theories were proven to be true. Actually, wouldn't orbiting satellites be similar to the aircrafts in the experiment? only now at a higher speed and altitude. In fact, the atomic clock is one of the core components of GPS navigation satellites. The clock needed to be calibrated according to the theory of relativity, believe it or not. Otherwise, the time on the navigation satellite would be 38 microseconds faster than the ground every day. At first, 38 microseconds sounds like nothing, but actually, a time error of even 1 nanosecond in the satellite navigation system will lead to a distance error of 0.3 meters. The difference of 38 microseconds will lead to an accumulated error of 11 kilometers per day for the positioning provided by the GPS. No one would dare to use a GPS with such low accuracy. Its guide might lead you into a ditch. Einstein regarded time as the fourth dimension to the three-dimensional space. Together they form a four-dimensional space-time. From then on, the concept of time became increasingly vague and mysterious. Time is no longer understood as absolute as described by Newton, but relative according to Einstein. Einstein told us that there is no single unified time. There are many different times. Each point in space-time has its own time, and time can be fast or slow. At this point, people started to think, if we go further, is it possible to change the direction of the passage of time and turn it backwards? It sounded like an aspirational idea, but soon a physicist jumped in and said, this is not in line with the second law of thermodynamics. Entropy is another brain-twisting concept. In simple words, scientists introduced this term to describe the degree of chaos. The more chaotic means the greater entropy. The law of entropy explains that everything in the universe goes through a process from order to disorder. The universe would end up with increasingly more chaos as time goes by, and this process is irreversible. When the degree of chaos, that is, the value of entropy, reaches its maximum, the system would be in serious disorder and finally come to its end. In the law of entropy increase, there is an objective tendency in nature to flow from orderly to disorderly as time passes. This is impossible to reverse. It's like a drop of ink in a glass of water. Soon the ink spreads to every bit of the glass. The ink changes from an ordered state of cohesion to a disordered state of chaotic distribution, and you can't make the mixed ink unmixed again. The law of entropy can be used to explain many observations in life. For example, your new cell phone will slow down with the passage of time, and a tidy room will inevitably become less tidy after a few days. Let's look at the development of the universe based on the law of entropy. As time passes, the entropy of the universe will continue to increase. When the entropy increases to the maximum, the universe will become a silent and quiet universe with no energy or matter movement. All life will die out. Therefore, many people say that this law is the most disparaging law in the whole universe, because as the law explains, the end of the universe is destruction, unless an external energy is applied to the universe. Similar to tidying up a gigantic room of the universe, the external force can restore the universe to order, so that the universe won't come to an end of destruction. Once the law of entropy increase was proposed, it made many scientists pessimistic, and many people launched a cross-examination of this theory. But no one was able to prove it wrong. That is, until the Poincaré recurrence theorem came out. French physicist, mathematician, and philosopher Henri Poincaré proposed the Poincaré recurrence theorem. He expressed the idea that the motion of microscopic particles, even if they are very complex and chaotic, will one day return to their initial state. For example, if there is a moving atom in a closed bottle, and the initial position of the atom is point A, the atom will return to its position of point A at some point in the course of its subsequent motion. Even if there were more than one atom in the bottle, the result would still be the same. At some point, they will all return to their original positions at the same time. Poincaré recurrence shows that the development of the system from order to disorder is a macroscopic process, but it does not hold true in the subatomic world. Instead, our world is made up of microscopic particles, and there are roughly 10 to the power of 80 atoms in the universe. It's enormous. The reason why the universe changes every moment is that the atoms are in different states of motion every moment. If we compare the universe to an oversized sealed bottle, since the atoms in the bottle will eventually return to their original state, can the whole universe be continuously restored? Of course, with this reasoning, the answer is yes. And scientists have calculated that the time needed for the universe to return to a certain state in the past is so many years. Don't even attempt to try and wrap your head around this number because it's an astronomical amount. It's displayed here. Although the time required for the Poincare recurrence is unimaginably long, so long that the current age of the universe approximately equals to 0, we can't deny that as long as the conditions are met, Poincare recurrence could happen. In other words, this means that the universe will reincarnate. In the infinitely distant future, the universe may revert to a singularity and have another Big Bang. Perhaps it's not the first time that we've met, but we've already met many times long ago. In the cycle of the universe, each person's life is a repeat. At this point, it turns out that it is really like Einstein said, the past, present, and future is just an illusion. When recurrence occurs, things that have disappeared will reappear, and people who have passed away will be reborn. But since the memory and perception of all lives will also be restored to the state of that moment, the reappeared life may not perceive that this reappearance has occurred. Here's a little hope for you all. In 2018, researchers from the University of Vienna in Austria successfully confirmed the Poincare recurrence phenomenon in a multi-particle quantum system and published the research results in the journal Science. The concept of reincarnation is often mentioned in theology, but scientists in the laboratory have now confirmed this concept. This may be the warmth that science brings to us. Perhaps after all, there is continuity of life after death, and perhaps there is meaning to life. You only live once may be a saying of the past as we come to learn more about the universe in which we live. Well, that's it for today's program. Thank you for watching. I hope you followed along, and I will see you next time.